We will now look at an important topic, and is that of the gradient in different coordinate systems. Many problems in physics have spherical or cylindrical symmetry, and knowing how to calculate the force from potentials in these coordinate systems becomes crucial. Not that they cannot be calculated in Cartesian coordinates, but it is far easier to calculate them using the expressions of the operator in these systems. We know that conservative forces can be written as the negative gradient of a potential energy function. Where the potential energy in general can depend on the x, y, and z coordinates. The gradient, the symbol that looks like a triangle, is the vector that contains the partial derivatives with respect to the Cartesian coordinates x, y, and z respectively. We shall use the shorthand notation for the partial derivatives, that is, a delta with a subscript indicates the variable that the derivative must be taken with respect to. So, using unit vector notation, the gradient in Cartesian coordinates can be written in the following way. The question is, for example, what about for problems, say, in cylindrical coordinates? Let's first remember the expressions for the Cartesian variables in cylindrical coordinates. It is important to notice that the c variable remains the same. The only variables that change are the x and y variables. So, if we were to use cylindrical coordinates for the potential energy function, how would the gradient look like in this coordinate system? We will first take the Cartesian coordinates written in cylindrical coordinates and invert the relations such that the cylindrical coordinates are written in terms of the Cartesian coordinates. It is worth mentioning that for this particular system, inverting the relations is quite simple, but it is not always the case for most coordinate systems. Before proceeding, Let's first make a diagram of how the coordinate system would look like in the Cartesian plane. We want to find the gradient in terms of the partial derivative with respect to r, the partial derivative with respect to theta, and the partial derivative with respect to c using the unit vectors r hat, theta hat, and z hat. For this, we use the chain rule for each partial derivative and then put the terms together. This is a long process, so we shall only do one single term and then generalize. Just as a quick reminder, the gradient in Cartesian coordinates is given by the expression we shall first look at the partial derivative with respect to x in terms of the new variables. For this, we use the chain rule. First, use the chain rule with respect to the variable r. Then, use the chain rule with respect to the variable theta. And finally, use the chain rule with respect to the variable z. It is important to notice that the variable z does not depend on the x variable, so the derivative of z with respect to x is 0. Now, we want to calculate the derivative of r with respect to x and the derivative of theta with respect to x. We shall first calculate the derivative of r with respect to x. To do this, we use the expression of the inverted variables, and then when we have the derivative, we replace the expressions for the Cartesian coordinates in cylindrical coordinates. Thus, we can conclude that the derivative of r with respect to x is the cosine of the angle theta. We will now use implicit differentiation to get the derivative of theta with respect to x. From the inverse relations, we see that the tangent of theta is calculated as the quotient between y and x. Thus, if we take the derivative of the tangent of theta with respect to x, we must also take the derivative with respect to x of y divided by x. On the left-hand side, since theta depends on x, we use the chain rule to calculate the derivative. On the left side, the derivative is negative y divided by x squared. Be careful with the negative sign, it is important. We can now use the trigonometric identity that the secant of theta squared is 1 plus the tangent of theta squared. This because we know that the tangent of theta is y divided by x. So now we can easily solve for the derivative of theta with respect to x. Thus, replacing the Cartesian variables by the cylindrical variables, we get that the partial derivative of theta with respect to x is the negative sine of theta divided by r. Thus, if we replace what we found and do the same for the partial derivatives of y and z, we get the following expressions. So, if we put everything together using vectors, we can rearrange the expressions to find the gradient in terms of r hat, theta hat, and k hat. The expressions for r hat, theta hat, and k hat are what we have already seen in class. If you don't remember them, look for them. Notice that the procedure to get this expression is not that difficult. It just takes some work. Thus, the final expression for the gradient in cylindrical coordinates is given by the expression Thus, the most important forms of the gradient you will encounter, at least most of the time, are in Cartesian, cylindrical, and spherical coordinates. By no means are you expected to memorize them, but it is convenient that you at least know how to get them. Also, remember to make a diagram with the meaning of the coordinates and the conventions that you are using. To give an example of how to find the force from a potential energy function in, say, spherical coordinates, we will use Newton's law of universal gravitation as an example. Newton's law of universal gravitation tells us that the potential energy between two particles of mass m1 and m2, such that m1 is at the origin and mass m2 is at some distance ρ, is given by the negative product of the masses multiplied by a constant. The potential decreases as the inverse of the distance between the particles. As I have already mentioned, the goal is to find the force associated with this potential energy function. Notice that I am now calling the potential energy function V of x, y, and z, or of rho, theta, and phi, since if we use phi for the potential energy, it can be confused with the angle phi, and we really don't want to do that. To find the force, we will use the gradient in spherical coordinates, since the geometry of the problem is that of a sphere. Well, at least to a good approximation. Remembering that the force is the negative gradient of the potential, we shall take the gradient and multiply the result by a negative factor. The first step is to write out the gradient in spherical coordinates, as we have already seen. Then apply it to the potential energy function. In this case, the potential energy doesn't depend on the angles, so the derivatives are zero. The only meaningful term is that associated with the distance rho. Thus, we can easily calculate the gradient, noticing that the final result is a vector. Finally, the force is the negative of the vector we have just found, and of course, you recover the force you must have already learned in your previous courses. We are now going to briefly discuss Hookean springs. Don't worry if you feel that this introduction is somewhat short, since we will have a whole section dedicated to this topic in the next lessons. We shall consider a block of mass m attached to a spring that is attached to a wall. The spring is massless and it is initially in its relaxed position. When the spring is stretched or compressed a length x, we want to know what the force and potential energy function are. It was in the 1600s that Robert Hooke, a contemporary of Newton, found that the force is proportional to the displacement of the spring from its equilibrium position, and it's always directed towards it. The constant of proportionality is called the stiffness constant, and it's related to how much a spring can stretch or compress per unit force. This relation is called Hooke's law in honor of Robert Hooke. We now want to calculate the potential energy of the spring when it is stretched or compressed. We can set up the integral to find the potential energy, remembering that the force is conservative and that there is a negative sign in front of the integral. Since this is not a constant force, we must perform the integral. You cannot say that the work done is simply the force dot producted with a finite displacement. So, first, write the force and the infinitesimal displacement and replace them in the integral. We will assume that we are starting from the origin, x equals 0, and moving an amount x along the x-axis, where x can be either positive or negative. Remember to use a different dummy variable for clarity. This is a relatively simple integral to make, and when doing so, we get the potential energy we already knew about. The question is, what is so interesting about this potential energy function? To answer the question, it is convenient to make a plot of the potential energy function. To do this, we will set a set of axes where the vertical axis represents the value of the potential energy at a given point x, and the horizontal axis represents the position x. From the expression for the potential, we know that this is a parabola. One of the important features of the parabola is that it has a global minima at the origin. The important thing to notice is that the force is related to the derivative of the potential energy, such that the force is the negative derivative of the potential energy and is directed along the x-axis. Always remember that forces are vectors. In this case, if we draw some tangent lines to the curve, we can see that the force will always point towards the origin where there is a minimum. Let's just write the value of the derivative at this point to see it clearly. This is consistent with what we know about restoring forces. The force will always point towards the origin, no matter the position of the particle. We can even make a more general claim. Conservative forces will always point towards a minimum of the potential energy function. Forces will always try to minimize the energy. However, we will be mostly interested in the cases where the derivative of the potential energy function is zero and thus the force is zero. So, if you have a general one-dimensional potential energy function, it may have a crazy shape like the one I will draw. Notice that this function has peaks, local maxima, valleys, local minima, planes, constant parts, and it might also have sudden changes of concavity, inflection points. In potential energy functions, these features indicate the points where the force is zero, and thus, using Newton's first law, they are points where the body is not accelerating. These are called equilibrium positions. Let's highlight some of these regions just to get a sense of what I mean. I will first highlight the regions of interest, and then I will discuss what they mean. The first regions I want to comment on are the regions of neutral equilibrium. Regions of neutral equilibrium are regions such that if you move towards either the left or the right of your current position, you will feel no force at all. Thus, you will not experience any force whatsoever, and you will remain on the point you have moved to. The second regions are the regions of stable equilibrium. These are the regions that represent restoring forces, or forces that will always attract you towards the point where you started from. Regions of stable equilibrium are regions such that if you move towards either the left or the right of your current position, you will tend to be pulled back to where you started. The stability of the equilibrium is determined by how concave or positively curved the valley is, and how far the curve extends. The third regions are the regions of unstable equilibrium. These are the regions that represent scattering forces, or forces that will always repel you from the point where you started from. Regions of unstable equilibrium are regions such that if you move towards either the left or the right of your current position, you will tend to be pushed away from where you started, towards a region of higher stability. The stability of the equilibrium, as for the stable equilibrium position, is determined by how convex or negatively curved the peak is, and how far the curve extends. In the fourth region, notice that if you, say, move to the left, the force scatters the particle. You feel a repulsive force, and moving to the right restores the position. That is an attractive force. Since the overall force around the region is a mixture of restoring and scattering forces, the equilibrium about this point is said to be undetermined. Of course, for 2 or 3-dimensional potential energy functions, it is more complicated, but the same arguments can be made.